Hi there, and welcome to our 7th video in this Integrated Math 1 Unit 1 video series. This will be our final video in this unit, and we'll start off as we usually do with our warm-up for today, which is actually only 5 problems this time. So take a second to work through these. Alright, let's take a look at number 1 here. What is the y-intercept of 2x plus 7y equals 35? This is in what we call standard form, but it doesn't matter what form we're in. The y-intercept is always the y value when x is 0. So when x is 0 here, we're going to get nothing out of this, right? So basically, some people like to just cover that up. So, but it's when x is 0. When x is 0, that is 0. So really we're just solving this here, 7y equals 35, so y is 5. So our y-intercept is 0, 5. All right, number 2, fx equals negative x squared plus 3x minus 1. What is f of negative 3? So we have negative, really want to figure out what negative 3 squared plus 3 times negative 3 minus 1 is. That's what we want to find out. Now be really careful with this first part here. Make sure you put your negative 3 in parentheses, because you're squaring whatever x is. X happens to be negative 3, so you want to square all of negative 3, not just the 3 part. So you have negative 3 squared is negative 3 times negative 3. That's positive 9. Times negative 1 out here in front is a negative 9. Here we also get negative 9, which is negative 18. Minus 1 more is negative 19. All right, number 3, how many extrema or maximums and minimums, crests or troughs, whatever you want to call them, but in general we call them extrema, could this quintic function have? So if it's got a highest degree of 5, it could have at most 4 extrema. I'll draw you a quick sketch of that here. So if we have a degree 5, it could have up to 5 zeros, right? It could cross the x-axis up to 5 times. So if it crosses 5 times, we'll just start down here at the bottom left. Crosses once, then I have to have 1 extrema to get back down to cross twice. And then to cross again, I have to have another extrema to get back there. And then 1 more extrema to get back down to cross for the 5th time. All right, 1, 2, 3, 4, oh sorry, 1 more, and 5. So there are 5 zeros, 1, 2, 3, 4, 5, and we had to have 1, 2, 3, 4 extrema to make that happen. Now there could be a fewer number of real real zeros or x-intercepts, and so because that we could have fewer extrema, but at most we could only have 4. Because think about what happens here. If we were to have another extrema here, we'd have to cross the x-axis again, and that would go against the fundamental theorem of algebra that states we could only have up to 5 zeros or x-intercepts, and so we can only have up to 4 extrema, which is 1 less than the degree or highest power. So because the highest power is 5, we could have up to 4 extrema. All right, number 4. A shirt that is 60% off costs $17.50. What was the original price? And so really what we're going to do here is, and I'll just set it up for you here, 60% off. So something, I'm going to call x here, some value times, let's see, 60% off. To do 60% off, that would actually be 40% of the value. So to get 40% of something, you multiply by 0.40. All right, that's 40% of its original value, or 40% of its original value, which is 60% off, equals 17.50. So you would divide 17.50 by 0.4. All right, and I'll let you finish that one off. Number 5, what is the end behavior of this polynomial here? Really the only two things that matter. I'm going to circle both things here. The first thing that matters is this coefficient here, which is a -1, and then the highest power or degree, which is 7. That's all that matters. In a couple of videos ago, we talked about there's 4 cases. There's up to the left, up to the right, down to the left, down to the right. There's down to the left, up to the right, and then switch them. So there's only 4 cases. In this particular instance, we have an odd degree. So that means they're going to go in opposite direction. So either down and up or up and down. Because it's a negative, okay, it's going to be opposite of the traditional odd power. So the traditional odd power, looks something like this. If you think about your power functions, either x cubed or x to the 5th or x to the 7th, those all have this general shape, down the left, up to the right. Because it's negative, it's going to be the opposite of that. So up to the left, down to the right. So as x goes to -infinity, or approaches -infinity, y, or f of x, approaches +infinity. So that's saying as we go to the left, the function goes up. As we go to the right, so as x approaches +infinity, the function goes down to -infinity. Okay? So as x approaches infinity, y approaches -infinity. That's talking about this arrow here. As we go out to the right, the function goes down. All right, so in this final video, if we think about what we've talked about in this unit, we started out with quadratic functions and looked at the graphs of those from factored form. And then we got into polynomial functions, higher degree ones, like cubics and quartics and quintics. And we've talked about the overall graph of those and how to graph those from factored form. And then we've got into more analysis of graphs. So we talked about transformations. We've talked about average rate of change. And in this final video, we're going to talk about how to solve polynomial equations graphically. Okay, so that's our goal for today, is to solve polynomial equations and inequalities graphically. So an equation is when you have an equal sign in between 2 expressions, and then inequalities when you have like a less than or greater than in between 2 expressions. So let's look at this situation today. So we're going to analyze this situation from a lot of different angles, including some equations and inequalities. So in this particular situation, we have Zorzanzas. It's a company that makes video games, and it's business plan through the first few years of business. So we have this function here that represents profit in terms of months. And notice the profit is in terms of dollars. We'll talk later, it's actually in thousands of dollars. But anyways, we want to think about this function and how it models these situations. So we want to think about where do these situations happen in the graph. So connecting the two together. So if we look at the graph, it starts out at a negative value, and then it increases, and then it decreases, and then it increases again. And some different points along this graph are maybe some interesting points in this company's history. So let's start with A. The chief executive officer anxiously meets with her accountant. B, the highly anticipated game Zenith 2 is released. The company opens its doors for business for the first time. The company reaches its first short-term sales goal. The company breaks even, and then a large conglomerate buys the company. So take a moment, and I want to see what you think. So where in the graph would these things maybe have happened? So you can just maybe draw a rough sketch of the graph, and then you can label the point that you think it happens with the letter that it represents. So take a moment to do that. Okay, so in the first one here, the account executive anxiously meets with her accountant. Probably anxiously meets when things are not going well. So if you put it maybe down in here somewhere, that would probably be about where that would take place. I'm gonna say maybe down here at maybe here. Let's say A is right there. The highly anticipated game Zenith 2 is released. So if it's highly anticipated, probably drove up the sales quite a bit. So I'm going to say somewhere in here when it starts to really increase there at the end. So maybe right here. And again, it doesn't have to be exactly where you put it, but somewhere in there. So it drove up the profit from there. The company opens its doors for the first time. So I'm going to say that's here at time equals 0. So before the first month goes along and that kind of thing. So it's at month 0. At time 0, that would be C. All right. The company reaches its first short-term sales goal just as the holiday shopping season ends. So if they reach their sales goal, that means they were doing pretty well. I'm going to say that happened right maybe in here where we have this relative maximum happening there. All right, the company breaks even. So this can happen actually at a number of places. I'm going to do this in blue. So this could happen here, could happen here, and it could happen here. So after the company started and they started to sell their product and they broke even there, or maybe when they started to lose money after that holiday season ended, or maybe after they were in a bad spot here and they started to sell Zenith 2, maybe they broke even in there. So there are 3 different places where the company broke even. So those will all be, I'll say that's E. And then I skipped a few here, and so we're going to actually go down to H. And a large conglomerate buys the company. So I'm going to say that happened here, maybe at the bottom here. So I'm going to say that's H. So they bought the company, and then they released it in 2, and then it drove up the prices from there. So that large company that bought this business maybe turned things around quite a bit there towards the end. So that just kind of gives you an example of how to relate a graph to its context and different things that happen in the graph. So let's analyze this graph even more. So we still have this same company here in their first 5 years of business. So now we're talking about years and not months. We've got the profit in thousands of dollars is the y-axis here. And we want to find out some different things about this graph and when certain things happened with this company. So for instance, when did the company reach a profit of $800,000? When did the company reach a profit of $200,000? Greater than $200,000? And then lastly, when was the company losing money? So take a moment and see if you can think about when those 4 things were happening with this company. Okay, so with $800,000, so when did the company reach a profit of $800,000? So $800,000 is right here. Okay, so if we think about this, I'm just going to draw a line along 800,000. So this line here represents 800,000. Did the company ever reach that point? Well, it didn't starting out, but then towards the end here, maybe closer to year 4.5 or so, they did. So right here, right, they had a profit of 800,000. And so we're just going to estimate, when that occurred. So every, see, this is going to be 5 here. So it's not quite to 5. It's a little bit over 4.5. So maybe we're going to say 4.6 years in is when that happened. And again, you may have something different, but as long as it's about that, then we're fine. All right, how about 200,000? So I'm going to outline this one again. Take a line here. I'll do this line in maybe green. So 200,000 is right here. So when did the company reach a profit of 200,000? So it actually happened a number of times, right? As you can see in the graph here, it happened, starting out, and then a second time here, and then a third time after we actually sold the company at the end there. So right about here, here, and here is when the company had a profit of 200,000. So let's estimate when that happened here. So the first one was maybe about, it looks like it's pretty close to half a year. So maybe 0.5 years in. Second one was not quite 1.5, maybe a little bit less than that, maybe 1.4 or so years in. And then lastly, not quite 4.5. 4.5 is right here, so maybe 4 point, I don't know, I'm just gonna estimate 4.35 years. So there are three, as long as you have 3 times about those numbers there, then we're good. So that happened 3 times. All right, greater than 200,000. So now we're thinking about when is it not equal to 200,000, but above, when does the sales go above 200,000? So if we think about it, it goes above 200,000 in between these 2 points that we just found. So in between we said this was 0.5, in between 0.5 years and 1.4 years is when that occurred. So in between, we can say in a couple different ways here. We can say when x is less than 1.4 but greater than 0.5, or we could say between 0.5 and 1.4 in interval notation. So that's one way to write it there. So when the time is in between there and there, or, the big or here, it was also above 200,000 to the right there as we get closer to 5 years. But anything where x is greater than 4.35 is what we said it was. Or you can do interval notation of 4.35 to infinity is when it's above 200,000. We're going to assume, we actually don't know that it continues to go up. We're going to assume it does given our graph here. Obviously things could change, maybe year 6 and 7 on down the road, but we're going to assume that it stays in that pattern that it was taking up there. All right, lastly, the company is losing money. The company is losing money whenever the profit is negative. And so when we think about that, that's whenever the profit is less than 0. So whenever P of T is less than 0. So if we draw a line here, I'll do this in red, along the x-axis. So whenever the graph is below that, then we know that the profit is negative. So that's going to occur from 0 to about, what we say it was, let's see, this is about 0.2 or so. So from 0 to about 0.2, or you could write an interval notation 0 to 0.2. And then it's also negative between, let's say, 1.75 and 4.25. So between 1.2, or sorry, 1.7, and 4.25. Or you could, again, do that in interval notation. So from 1.75 to 4.25. And of course, it'll be in this interval or in this interval. But hopefully that kind of gives you an idea of how to analyze a graph and think about where are things equivalent to certain values, but also when are things above or below certain values, because we also want to think about that as well. So when it was equal to a particular value, we're talking about an equation, right? When is this function equal to those amounts? Whereas down here, we were thinking about when is it greater than, so when is this function greater than 200,000, or when is this function less than 0? So we're talking about inequalities down here at the bottom. All right, so kind of a graphical approach to solving equations and inequalities. I want to go back and review average rate of change real quick from last video. So just kind of give you a chance to practice it a little bit more. So here we have the same function, and we want to think about, or at least estimate, what the average rate of change is between 3.25 and 4.25. So in here. So let me give you a chance to at least estimate what the average rate of change is between those two x values, 3.25 and 4.25. Okay, so again, average rate of change is the slope of the secant line between the 2 points. So on average, how are we increasing in terms of our profit over that interval? So we want to think about our change in profit over change in time. So because the change in quantity over the change in time, or the slope of the secant line here. So our change in profit would be 0. Right, we have a profit of 0 here, minus, what was it before? This is 400, this is 800, this is negative 600. So negative 600 over the change in time was, we said 3.25 and 4.25, so it'd be 4.25 minus 3.25, which would give us a change in profit of 600 divided by a change of time of 1. So really, our average rate of change here is 600, which is the slope of this secant line here. So that'd be 600, and I'm going to write this here, $600,000 per year. So if we think about our units there, it'd be that in thousands of dollars per year is about what we're gaining there, at least if you estimate. Okay, so let's give you some other examples. Let's go back to solving equations and inequalities, and let me just throw an equation at you here. So we have a quartic. This quartic polynomial equals 4. So the question is, what value of x makes that occur? And if I were to do this by hand, I don't even know where I would begin. All right, but we know that we have the technology, and the graphs that can help us do this. All right, so let me pull up Desmos real quick. If you haven't used Desmos, you can just type in desmos.com and go there and hit calculate. So all of this that I'm going to do on Desmos can also be done on your TI calculator as well. So that's fine. All right, so I've got our two equations here. So if we think about graphing the left side, and then I'm going to graph the right side and see where they intersect, right? When is this equation at 4 in terms of the y value? So again, going back to the video game example, like when did it hit that value, right? So when does this hit a value of 4? So we have the graph here. This is the graph of our polynomial, our quartic, which makes sense because it looks like it has 3 extrema, right? 1, 2, and then 3 up there, which means it's at least a quartic, and that's exactly what it is, if you can see my function here. So I'm graphing this function right here, right now, and then I want to graph the function y equals 4 to see where they intersect. So if I graph y equals 4, I can see that I have 3 solutions to this equation. And they are, and on Desmos, I can just click these values and they pop up here. One solution is negative 1.618. One solution is negative 0.3333, maybe even estimating negative 1/3 there. Another solution would be positive 0.618 and positive 1. So notice I'm pulling out the x values from these points. The y values are not really significant here. I want to know what x value satisfies that equation, right? Those are the solutions to that equation. So there are 4 solutions to that equation. And I didn't have to do any algebra necessarily. I was just graphing the 2 to see where they intersect. All right, so let me give you a chance to try one. Actually, before we do that, let me show you one other way you could have done this. When solving an equation, sometimes it's advantageous to set it equal to 0. So if we were to do that, we'd subtract 4 from both sides, right? Subtract 4 from here and you get 0, subtract 4 from here and you get negative 1. So we have this new equation, right? It should have the same solutions though, right? If we subtract 4 from both sides, it still should have the same solutions. So if I do that here, here's my new graph. So there's the graph there. And then now that it's set equal to 0, I'm wondering, where does it cross the x-axis? Where does this green graph here cross the x-axis? Where does it hit 0? So if I highlight these points here, I get the same solutions. So sometimes you might want to do that, especially if you're using a TI calculator. You might want to do that sometimes, but just know that that's an option, right? So if you're using TI calculator, you can use the intersect feature and do the same thing that we're doing here. So under second calc, I believe it is, intersect, and then you can hit enter 3 times when you cursor over close to the point that you want. But you could just pull up Desmos and look at it there. The key idea here is that we're trying to find the intersection between the left side of our function or our equation and the right side of our equation. And where do those intersect? And we can do that here. So let me give you a chance to try this one. So we have a quadratic equals a linear function. So see if you can solve for this one graphically. See what you can do. All right, so if we do this graphically, we're going to graph the quadratic equation, which I have here in red, and then we're going to graph the linear one, which we have there in blue. Let me make it a little bit better for you to see here. Okay, so we have the quadratic in red and the linear in blue, and I can just click here. And I can say, okay, where do these intersect here? Looks like at -3, -18, and at 217. Again, I'm not worried about the y values, I'm only worried about the x values. So an x value of -3 makes these equivalent, and an x value of 2 makes these equivalent. So -3 and 2 are my solutions to this equation. Let's confirm that algebraically. So again, when solving an equation, a lot of times you want to set it equal to 0, especially when you have a quadratic, so that you might be able to factor it. All right, so we have x squared. And we subtract 7x from both sides. So 7x minus 7x is 0x here. 8x minus 7x is just 1x. And then we're going to subtract 3 from both sides. 3 minus 3 is again 0. -3 minus 3 is -6. And now we've got it set equal to 0. So if we can factor here, we can actually solve this pretty easily. So this is going to factor, let's see. X times x is x squared. And then these next two, x times this one and x times this one, are going to be both like terms. They're going to add together. So we want these to be adding to give us positive 1x. But then we also need to think about when these two things multiply in the end, they need to give us -6. So we need to think about two numbers that multiply to give us -6, but then in the blue here, add to give us the positive 1. And let's see, -6, let's see, the factors of -6 will be 6 and 1 or 3 and 2. 3 and 2, we can make that happen, right? To give us a positive 1 here. So it'll be positive 3 and -2. The order doesn't really matter there. But that's going to work out to give us that back. If we think about that in terms of reverse distribution or whatever. So what values make this happen? So if we think about -3 from this one and positive 2 from this one. So x equals -3 and 2. All right, if we plug in -3 for both x's here, we get -3 plus 3 is 0. Times -3 minus 2 is -5. 0 times -5 is 0. So that works, right? -3 works. How about positive 2? Positive 2 plus 3 is 5. Positive 2 minus 2 is 0. 5 times 0 equals 0. So both of those satisfy the equation, which makes sense given what we saw graphically. All right? But this idea, like, we're looking at polynomials here, But really this idea works for any function type ever. Okay, you can always graph the left side, graph the right side, and see where they intersect. If you're using a TI calculator, you can graph the left side, the left side of the equation in y1, the right side of the equation in y2, and then use the intersect feature. Of course, in Desmos, you can just click the value. So I want to give you a chance to create your own. Create an equation and see if you can find the solutions to that. Okay, so I created one, just kind of a crazy looking one, just to kind of emphasize the point that it doesn't matter what the equation is. You can always graph the left side and the right side and see where they intersect. So I've got this fraction here, absolute value there. I know it's weird, but let's just go to Desmos and look at what we have here. I've typed in the left side here and the right side here so that I've both graphed on the same plot here. The red one is the crazy looking fraction, and then the right one is the absolute value. And I want to see where they intersect, so what x value is here. So x value of, looks like 0.181, and an x value of 1.787. So I was able to solve that equation really quickly just by looking at the graph and seeing where they intersect. Obviously, we can do inequalities as well, as we've seen back in the video game example. Just looking at the interval in between what two x values that does satisfy that inequality. So when is it above or below a particular value is most often what you'll see. Okay, so long story short, I hope that you've been able to see how to solve polynomial equations and inequalities graphically, and we're going to look at next unit more algebraically. So can we solve these polynomial equations, or at least some of them algebraically, looking more into factoring, looking more into multiplying and dividing polynomials, those kinds of things. So we'll do a lot of that next unit, but hopefully you were able to get a sense of what the graphs of polynomials look like, their end behavior, increasing and decreasing, and those sorts of things. And so that concludes our first unit in Integrated Math 1. I hope to see you in our next unit, which will be on the algebra behind polynomials. We'll see you then.